Okay, seems good. So let's try to be sharp on time, then I can still attend the talk I need to attend. If not, that's okay, not a big deal. So who starts?
I am.
Okay, very good. And just remind us before you start which paper it was. So it was the one on the exotics, right?
Yeah, it was the one you suggested, the quark hadron review.
Okay, very good.
That's the I remember.
That's okay. Okay, very good. So we start with Francisco.
Okay. So the paper I'm going to present is basically a review on some recent advancements in understanding the quark hadrons in the large N limit and sort of how it relates to the phenomenology of tetraquarks. So originally, Coleman, in his Irichi lectures, which are compiled in the Aspects of Symmetry book, he made an argument about the non-existence of tetraquarks in the large N limit, and it basically goes as follows. You have some interpolating field generally, which could in principle create a tetraquark in the vacuum. Generally, an object like this. Oops, and then you can use Beer's identities to rearrange this into some product of two bilinears, right? So, X, where Bi is some color neutral object like this, right? And then gamma I will be just a matrix that gives the spin flavor identity of this bilinear. It could be gamma phi, gamma mu, whatever. So if we want to understand the dynamics of this, we should look at two-point functions, right? So let's try to understand what we can infer from an object like this in the large N limit. So if you place this in here and then you would contract the fermionic fields first, you can classify the contributions to this into two forms. You have first one that connects, that's the double trace, which is an object like this generally, right? Which is basically I'll make the diagram, so let me just write it down. So generally, an object like this, where this index basically just signifies path integration over this field, and then so you have first an object like this, e_k x, e_k y, and then you integrate who. And then you also have one which is a connected diagram with all of them, right? And we'll basically just omit for the sake of so an object like this. So what does this look like in the large N limit, right? So this first contribution will be done, I'll identify this whole line as x, just for the sake of clarity, and this whole line is y. So the first one is an object like this, right? Where you can have whatever glue lines inside, doesn't matter, but you can have things like this in the leading contribution connecting the two. Whereas the second one will be an object like this. So Coleman argues that if this first one can never give us a tetraquark pole, because there's no interaction between them, you can sort of cut this and it require Clark confinement, and you have no you can never have a tetraquark, it's always meson pairs. And, however, this one, in principle, you could. But because there are no blue lines in the leading contribution, because if you add them here, you reduce the power of n, this will have an n squared, this will go as n squared, whereas this one just goes as n. Right? So the conclusion he made was that, well, this one dominates with a factor of n over this, therefore in the n to infinity limit, there's only this, and there can never be tetraquark poles. However, in 2013, Weinberg noticed that perhaps this argument isn't quite as conclusive as you'd like. The idea is, let's think about meson scattering, for example. You have two mesons that are scattering. The diagram will be basically this, except these points won't be identified anymore for the leading contribution. And again, you could say that the leading contribution dominates, and then you have no scattering at all. But this is, so they don't interact, you have just two meson pairs propagating in large n limit. But this isn't particularly interesting for the sake of understanding how the interaction vanishes, right? You can just say, look at this and say, well, at n equals 3, there's no scattering, because we know there is, right? So what Weinberg suggests is instead of looking at the limit here, we can calculate the amplitude first, and then apply the limit to look at how the interactions vanish. So to understand this point in the context of mesons, suppose you have 2 bilinear scattering, like you'd expect from meson scattering like this, then LSC tells us that the amplitude of such a scattering will be given by a product, and then you amputate the external x, so it's like this. And then you have a factor of renormalization, and you have the 4-point function, right? Crucially, this field strength normalization is related to the 2-point function. So, for example, for our BIs, we have something like this, right? BI, so 2 B's. This will be something like I z b over b squared minus m squared plus psi epsilon plus contributions from cuts and poles and whatever other less relevant contributions. But this, as for for the propagation of a bilinear, will be something like this, right? Just leading, right? And this goes with a factor of n. So this means that ZB is proportional to n. So for the case of a meson scattering, one could look. You're not supposed to look at this for this particular case because since these points are all different for this situation, then this just gives a disconnected term that's this part of the S matrix, right? It's the trivial part, so it doesn't go in the LSC contribution. So we have this, or the analogous situation of this where these points aren't identified. And then what LSC tells us is that you get a factor of 1 over root n to the 4th times the n contribution here. Or in other words, this goes as 1 over n, right? So now you clearly recover the idea that there's no scattering in the n to infinity limit, but you understand the width and how the behavior vanishes, right? And this is sort of more illuminating, especially if you want to talk about finite n situations, right? So notice that if we had taken the limit before, then we'd get a equals 0, right? Because this would have dominated, this is 0 compared to this, and we get nothing. So let's understand how the idea, how to apply this idea for tetraquarks, right? So for tetraquarks now you have some Q that goes to 2B's, right? In this situation now, what we're looking for is, so the 3-point function will be again, you'll have some product of traces. Wait, so this will be BI of x, BL of y, and then BK of y, x, and now some BK of z. So this is the first one, and then you have the connected term, which is the analogous of that one, where you have TQBB, right? So again, ZQ goes as n again for the same reason, and so let's try to look at this. Perhaps naively, one would look at this, and looking at this first term, you'd have, this goes as n squared, like we discussed already, and then if this goes as n squared, then we need to, now we have a 1 to 2 scattering, so instead of a 1 over root n to the 4th, we get a factor of 1 over n to the 3 over 2. And then when you multiply this by n squared, you have root n, in which you have, and then you conclude that the width goes as n. So perhaps tetraquarks are just wide states that are not observable, but this is not precise, not right. And the reason why is because, again, this contribution can never give us tetraquark poles. So when LSC comes to amputate the leg, this will kill any contribution that doesn't have the precise pole of the tetraquark contribution. So it'll just kill this first term entirely. So if there is a tetraquark, it'll be here. And if it is indeed here, you get a contribution, a factor of n. And then this goes as 1 over 3 over 2 times n now, which is 1 over root n. And then the width is 1 over n. So tetraquarks are stable. They're just in the n to infinity limit if they exist. And this is very different. And even if you make assumptions on the flavor structure of the tetraquark, you can even be more. You can find, for example, n squared for when all the flavors are different inside the tetraquark. So this is really nice because now we can understand the behavior in the n to infinity limit without, which can then lead to, we can make phenomenological predictions from this and perhaps lead to better understanding of when tetraquarks can show up. So this is
very good. Okay. Well, thank you. Just okay, 10 minutes, right on time. So questions?
So I got a little confused. You said that currently taking the origin limit and computing the amplitude, they do not commute.
Yeah.
The two. But I mean, I don't understand. Like for me, we just threw away those subleading diagrams because we were only caring about the leading ones.
Yeah.
So in principle, I don't know what's the
point is precisely that. It's when if you prematurely look at diagrams and find the leading one and discard every other one before looking at the amplitude structure, you lose information. But that's the point. So for example, here, if or the meson scattering, for example, right? If I looked, well, this is a leading diagram, and then I don't care about anything else, then I lose the understanding of how this structure goes away. And similarly here, if I look just at this, which is the leading diagram, then the LSC will kill this, and we get nothing, right? It's just a statement that we need to be a bit. It's not necessarily that it doesn't commute. It's more so the sense that we need to put everything on the table before we take the n to infinity limit.
Why did you compute B to B?
Oh, wait, here. So this was just a statement about how it would work for meson scattering. Because, for example, if we have two mesons scattering to two mesons, then you have one of these bilinears. Each one of these bilinears would be responsible to be associated to one meson, right? So you have this at a position and this one at another position is scattering into two other ones of these. So you have B1, B2 to B2, B3, B4.
But this is related to tetraquarks?
I mean, not directly. I was just sort of trying to explain the sentiment in an analogy first to mesons, which is more familiar, and then to tetraquarks.
And the general conclusion is what? Is that tetraquarks
Are stable in the large unit. If they exist, they're stable. They're there.
because the gamma goes on a red.
Yeah, exactly. In the n to infinity limit, you have the decay rate goes to 0. Right? It doesn't decay to 2 mesons.
What is that?
It's an antisymmetric tensor.
So epsilon ABC is a fully antisymmetric tensor.
Yeah.
What is that? Or what is it? What tensor is it?
It's Leibniz tensor, right? I suppose is some epsilon. So if it's 1, 2, 3 or anti-cyclical permutation, you get 1. If it's anti-cyclical permutations, you get -1. If you get repeating terms, you get 0.
So what is the large three values, 1, 2, 3.
Right, because these are polar indices, right? And then, well, then you have in the larger end limit, then you have any, I suppose, wait, that's a good point. When, well, I suppose the structure should stay the same, right? If you have this number bigger than the ones preceding, or any cyclical permutation of that, then you have 1, and then if there's a repeating number, then you get 0, and if it's not, if it's, for example, these two swap, then you have -1. So I suppose the structure stays the same, except these numbers range from different, they are not necessarily 1 to 3.
Where would such strange tensor come from?
I'm not sure if I can answer that.
Why do we contract tensors with other tensors and tensors with vectors?
Because we want to build scalars, right?
So why would that tensor that you just mentioned be relevant in SUN?
Because you're trying to build a color neutral object, right?
Good. So how would that tensor that you populate would transform under SUN transformations?
I suppose under, well, if it's generally a transformation under SUN is, you have, let me see if I remember this, it's been a while. It's, you'd, I see what you mean. You're saying that if this is a transformation, if, so you have some, first you have here that you have the derivative of the other term, you're saying that this is an n by n matrix, and then this needs to be n by n in order to make sense, for the multiplication to make sense. Is that where you're going?
Yeah, I'm thinking. So what would you like to check that this is a scalar? So which objects are transformed in an easy way in your expression?
Oh, the quarks.
The quarks, right? So the quarks, we know how to put a bunch of matrices there, right?
Mm-hmm.
And then what would you need to check for these epsilons?
Well, you need to check if the transformations cancel, right?
Yes.
So, I
Maybe said differently. So let's imagine we have quarks, and we could use different notation, but normally we think of the anti-quark with an index down.
yeah, right.
So normally it's more convenient. And now you have this representation. Now forget about the epsilons, right? But you have 2 indices up, 2 indices down.
Yeah.
So what could you do with this object if you want to construct a scalar?
Could interact it with glue, right? Glue in it, right? Could have an A.
You have other tensors that you can use. What tensor can you use to contract an index up and an index down?
Generator, right? T, for example.
Ease, for example. Okay, I was thinking just of delta AB.
Sure.
Anyway, so what tensors with 3 indices appear when you study Lie algebra?
The structure constant.
Yeah. Do you want to revisit your answer to what epsilon is?
Epsilon is a structure constant, right?
Right.
Okay, I see.
Which for SU, yeah.
Right. I see.
I'm not sure I buy this argument because you would have to show that the last object has a pole, and in the large n limit we showed in the lecture that it doesn't. So just seeing how things scale, I confess I cannot pinpoint exactly that step is wrong or something, but so okay, first there's a technical thing. The first line has 4 bits.
Yeah.
Right? No, sorry, that's fine. So that's fine. crucial to estimate even a 3-point function of 3 mesons. We could not directly extract immediately gamma, right? If I just give you a 3-point function, 3 operators, each of them that has overlap with a meson, what else do I need to do to be able to convert that into a 3-point function?
So, sorry, can you repeat that?
Suppose that I give you a 3-point function of 3 operators, each of them has overlap with a meson.
Sure.
I just give you, here is the 3-point function. It is n to the 7 halves. How do you from there extract, could you from there extract the coupling of meson, meson, meson? If I just give you a 3-point function like this, I just say I computed the 3-point function and I got.
So you're saying just an off-shell 3-point function?
Yeah, I just computed barium, 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 and I got n to the 7 halves.
No, you couldn't.
What would be the second step that you would need to do? What else do I need to give you? Not just the 3-point function, but also.
Well, you need to give me. Well, yeah, I need to know. Well, if I'm gonna extract some form of coupling, I need to. Wait. I'm not sure if that's what you want me to answer, but well, I need a scale, I suppose, and I'm not entirely sure.
I'd say, I have an operator that generates, that has overlap with the meson state.
Sure.
And I compute the 3-point function of these operators, and I got that the 3-point function of these operators give me n to the 10, and therefore the mesons couple super strongly.
You need to know that there's a pole inside the diagram, right? Because if
the 3-point function?
yeah, right. Because no, not in the 3-point function, no.
So how did we extract in class the coupling between pi and pi and pi?
You looked at between pi and pi and pi. The part of the effective field theory was a bit nebulous for me, but we looked at. Let me see if I can remember. We showed that we initially had. Let me remember now because I just focused so much on this event. Sorry for about the plan.
Okay, well, let's move on. The answer I was looking for is that you need to normalize the 2-point function, right?
Okay.
Just the 3-point function is not enough. So here I did not see where is the normalization of the tetrapart 2-point function.
But you normalize it when you apply LSE, right? That's what you're.
You were extracting some gammas, that was not clear which gammas it was, but you never normalized the tetrapart 2-point function to make sure that you know how from that cubic, where is it?
Here, right?
Where did it go? Aha, okay, sorry, I missed that. So Z cube was like n.
Yeah.
Okay, good. Okay, cool. Let's move to the second one. We are a little bit late compared to what I wanted. Thank you. Let's move to the second presentation. What paper were you talking about, John? Remind us, please.
Structured finance.
Structured finance. Very good. Leonardo and John. Okay.
called Bootstrapping Plans at large N, and the goal of the paper is to bound the low energy couplings of the ion effective field theory at large N. And the motivation for this, they say, is to try to solve QCD at large N. Putting more precisely, the idea is that you bound the space of, you map the space of theories which are healthy in some sense and which have a large N limit, and then you try to guess where QCD lies in that space. So the starting point is that we have an SUN in English theory plus some quarks, which are masses. And here I'll be discussing the case where you have two flavors, but in principle you can generalize these results to any number of flavors you want. So the idea is that you'll study 2-to-2 ion scattering and try to get some intuition from try to learn something about these couplings by looking at the behavior of this 2-to-2 scattering. So in class we saw that for large N, the leading diagrams are planar, or that they have a basic topology. So we have something like this. So we put a line here, line here, and a line here. And you don't have stuff like little tubes going on or like a loop inside here. It's just a tree diagram which has the topology of a disk. And we also saw in class that not all isospin channels are present. So what this means is that we have this statement about exotics flowing in the middle of this graph. So the only thing that happens when we cut the graph here is that we also get a mess. Okay, so from these considerations, we can just say that a general expression for this amplitude is something like this, which is something theory vector here times amplitude, which depends on the Mandelson variables, and we have some variable vectors times this one, plus something like times another amplitude, and you go switching all the S to U's and so on, changing this with the other vector. So this amplitude is not. It is only crossing symmetric for the exchange of the two variables which appear here, but it is not fully crossing symmetric because we are ordering the color indices by assigning the legs. So since the orbital goes like something like this, we don't expect the full amplitude to be fully crossing symmetric. Okay. So this is the first thing we know about large N that we're going to use, and then we are going to take a few more assumptions from the which do not come from large N, and then we'll try to bound these cooking constants. So we'll use three assumptions. The first one comes from unitary. So if we do a partial wave composition of the amplitude, like this. It is a statement about requiring unitary that these spectral densities here are positive. So this is the first assumption we get, and we will see that this is related to requiring that the cooking constants are positive. We also get an assumption about the rate of behavior of the amplitude at large S's, which is basically that at fixed U and at large S, the amplitude goes like this. And finally, analyticity. We require that and this U is analytic away from the real. So using these three assumptions, we can write some equations which are called dispersion relations. So we write this equation. So this is true because of this requirement here. And since we assume that n is analytic away from R, we can reduce this expression to something which is like this. I'll explain a little bit what this means. So this statement, that this version becomes this relation. Suppose you're in the S plane, and you have some, there possibly a branch right here at n squared, which is to be thought as the mass of the first resonance that you get in the pi-to-pi exchange. And you start with a contour integral here from this equation, and then by using this analyticity statement, you can reduce the integral to this contour. This second contour is basically this side of the integral, where you get the high energy behavior of the amplitude, and this low energy behavior of the amplitude is here. Now we use the final argument from the final property from Largen, which is to say that we are restricting the low energy amplitude to tree level, and from this we say that we can write this amplitude at tree level as some sum of the floating constants, which appear in the effective action, times polynomials of S and U. So if we were not restricted to tree level diagrams here, we'd have some other behavior which includes branchlets and so on. But since we are doing Largen in the second class that only the tree diagrams are leading, then we can use this the idea is to use this equation, plug it back here at this envelope, and use the partial wave decomposition for the general form of implied. And this provides us with a relation between the coefficients in the low energy effective action, which are here, and the high energy or UV degrees of freedom of the theory. And from this, you will get some equations, which are, I mean, I don't think I have to write them, but we'll get some rules. We'll get some equations. G. So this is these brackets mean that we're evaluating this partial wave, this polynomial, and this thing. And these G's are the G's for the different direction in the low energy effective action. And we also get some null constraints, which relate these different polynomials with one another. And the idea is that you take both of these equations and then you construct to find the allowed values to find bounds for the G. So that's very good.
Questions? Translation?
I understand the you erased it, but you had sort of three properties that you were sort of imposing, right?
Yep.
You had the analyticity, unitarity, and Rangine behavior. So what's sort of the motivation for this item, for the Rangine behavior?
Yeah, so in the paper, they give some reasons. It's basically an assumption. So I wrote it like then over S1 here. So if you take S0, you see that it is wrong, and you end up losing this, contradicting this equation. It would mean that you have some poles which should not be there. And if you go to S2, which is apparently you would, it is something that is justifiable from just QCD. This is called something like the Pomeron trajectory. But the point is that this Pomeron trajectory or this type of behavior would be related to exchanging gluons. And exchanging gluons would be having a diagram which has this little tube going on here, or something like this. Something like this, and we saw that this is not what we get in large limit because this is exact factors of one word. So, and I mean, basically they say that since this does not work and the other one it does not work, it is safe to assume that the behavior is like this. But I mean, I've seen some it is not, as far as I understand from the way they put it, it's not completely justified. It's not derived from any other principle. It's just an assumption.
More questions?
Usually when I see
this M should be the, we start with massless pions. So this M is not like 2 times the mass of the pions, it's just the mass of the first mass resonance of the first part of it.
Why is it a cut?
Yeah, they assume it's a cut.
Why would they make this assumption? How could you justify putting a cut?
Okay, so in principle, as we learned from class, that there should be just poles here, right? So the idea is that they want to be agnostic about the behavior of the UV theory. So they don't want to impose anything other than the 3 things that I wrote there, that it's unitary and analytic and so on. But yeah, in principle, you should just have discrete poles, but they want to define precisely what is, another thing that they want to find is the behavior of the function in this regime. So they want to impose as little as possible, and then the thing is that they say that it's a cut.
Could you imagine a function that has a cut becoming a function with poles? How would that work? Suppose I have a function whose discontinuity across the cut is f. How would you write immediately such a function with a discontinuity on a cut f of s? Can you imagine an integral representation that automatically gives a function with that discontinuity? So
You have,
let me give you a hint. Log, I can write as integral dy over x minus y. And that has discontinuity to pi.
okay.
Right? So now instead of 2 pi, I want a general function. What do I write instead of integral dx over x minus y? So that could have a discontinuity when I'm in y, as a function of y, that has a discontinuity, that's 2 pi r. If I start at some m squared, that integral, suppose the integral goes from m squared up to some big of lambda, say. Then at m squared, starting at m squared, I have a discontinuity equal to 2 pi r. Do you agree? How would I make it such that the discontinuity instead of 2 pi r would be a function of y?
So just put some math here.
Yeah. F of?
One.
No.
Sorry.
F of x, right? So, and now how would that expression become a sum of poles? Starting at m squared, and then a bunch of poles all the way to infinity.
Just expands.
Expand. What kind of f would make that expression into a sum of poles? Suppose I want a pole at m2 square, a pole at m3 square, a pole at m4 square, like Rodrigo is saying, because that's what we expect for an number. Well, what?
So I'm using meromorphic function.
It's simpler than that. Imagine I want a single pole at m5 square, where m5 is some value between m and lambda. I just want that function to give me a single pole. What would I put for that f? Okay, for the f of x. What f of x would you put such that the integral, our goal, let's put equal sign, equal 1 over m5 squared minus y. m5 squared, some m tilde squared, not m squared, it's not m squared, it's some m tilde squared minus y. What function would you put for f of x to get a pole? what's happening to the to x? The integral.
Sorry.
So y was interacting with x, where x is in a range, and now suddenly on the right, y only interacts with m squared. So what happened to all these other interactions of y with all the other values of x between m squared and 1? They just disappeared, right?
Yeah.
So what function does that localizes things?
Delta.
Yeah. So what f would you put?
Ah, okay. I see. It's just
Right.
m squared.
And if you wanted many masses, what would you write for f?
Some type.
So if you want to be agnostic and say, I don't know where the masses are, you can put a density and say that then the solution will put a bunch of peaks
Oh, sure.
where the masses are. Because I don't know where the masses are, right? If you don't know where the masses are, you could say, let me put some density and allow dynamically the poles to know where the masses are.
When you expand the expression that I wrote before for this, so I have something like this. So, and let's go with that. This is going on here. This would be equivalent to
Sorry?
so before I expanded the m is this. So this is a numerical vector times the spectral density times this polynomial. This would be having this thing would be about spectral density.
The spectral density would be the function. And then it would automatically reduce what they expect. Very good, let's next one. Again, what paper will it tell us about?
Ions and large energies.
Ions and large entity. Ions or baryons?
Fine.
Ions. Who's that paper by? Can you remember? Weinberg. But not it's the other Weinberg.
No, this is.
No. You thought it was the same Weinberg, that's why you picked the paper.
No.
How sad you are now. No, it's the same. No, that's another Weinberg. Yeah.
No, it's the same one.
What's the name?
Even fine.
Ah, it is. Okay, oh, very good.
This is related to.
Okay. So let's start here.
So let me give a motivation for what I'm going to do. So we saw in the very last lecture in PCD, and PCD is some motivation, for instance, nihilation, electropositon, and in general it works well for high energy physics. So in general, you cannot study, you cannot put the group constant small. So to study process of, for instance, moderate energy. So you can construct a effect field theory of quarks, gluons, and pions. But in this case, as you saw in lecture, you will construct a theory by something that is a vector theory, but there's infinite number of vectors, each one with additional factor of 1 over n square root. Therefore, this vector field theory is used to study low energy. Because if you want to study moderate energy, not very high or not very low, you have to consider all terms, because in general all terms contribute to the moderate energy. So the question is, how theory of gluons, of quarks, so massive quarks, and additionally you will put pion. So now pion is a really a field of it's not coming from these other quarks. You have composite mesons other than pions, composed of mass quarks. But now you have the massless pion, which in this case will be the boson associated boson of this quark. And you also have a interaction between quarks and the pion. This is the SU2 flavor matrix. So, and then you have also this is the covariant derivative of the pion. And in here there is no interaction with gluons. This is just covariant derivative with summarize the expressions for pion. And okay, and this is a constant. This is a constant. Sorry. There is a factor here, which I will not mention, but it's important for the hypervariate divergence. And the point that the Lagrangian stops here, and you can try to study moderate energy phenomena. And the point now also is that, as you saw, G scales as one of the studies of them. There is also this factor, this new constant, which also factor, which is also of order 1 over n. Okay, so now as you see here, there is an interaction between the pion and the quarks. So let's do similar thing we did in lecture, but now for this effective field theory for moderating. Therefore, if you consider a meson, you could consider the same process that we considered, and if you have a meson, two-point of meson. And now, you start doing the same thing as in pure PCB by putting some interactions. For instance, this one. So, as you saw, if you pick an intermediate state, this will also always be a meson. Okay, what now if you study this effective field theory, adding some insertion of pions? So we will have insertion of this pion here, external pion. But you also could have insertion of pions of this. So in principle, you could have exhausted intermediate state, because this is a product of two mesons. There is the meson pion here and another. So in this case, we will not be happy with it. But let us do the same analysis using large n. So the point is that in general, you can count the number of ends of a diagram in general by the characteristic of the rule given by vertex minus internal lines plus faces. So in general, you have this kind of diagrams, and this is a face, gives a factor of n, and this combination gives the other. So this is the vertices and this is internal lines. So this will be important because now that I add pions, I would in principle change the number of factors of n's. So this will change in principle by this formula here. However, I would emphasize that pions have no color. And therefore, the factor that comes from the face, which is turns into a loop, which relates to a loop, disappears. So this is the variation of the number of factors of n. And remember that the number of loops is equal to I minus v plus 1. And therefore, you can identify this as variation of loops. Therefore, you have that variation of number of n is equal to variation of n. So, when you increase the number of loops by pions insertions, you decrease the number of factors of n. And this happens because when you have a loop, you have a factor of n. When you put another loop here, you kill this n because there's no color in the pi. Therefore, in large n, if you want large n, the dominant diagrams would have variation of loops equals 0. Therefore, in large n, the consequence is that you could not have these insertions here. And you only have external pions. And therefore, you conclude the same thing, that you have no exhaust. There may be intermediate states. And just to finish, there is another consequence, there is another subtlety here, which is different in ESG, that you could have diagrams of this form. Could have disconnected diagrams. And then connected by pions. And here you also have possibility of having an exotic state. But now the number that I mentioned will change by delta V minus delta R. So if you have initially a number C of disconnected diagrams, you want to go to 1 connected diagrams, and the variation of C is equal to 1 minus C. So this changes how you count the number of n's, factor of n's. So this is equal to minus delta L plus 1 minus C. Now again you have the same thing happening. When you increase the number of loops here, you decrease the number of L's. So delta L equals 0, and also delta chi equals 1 minus C. And let's count the order of the diagram. In each loop you have n. So you would have n to the C times n to the variation of number of n's, which is 1 minus C. And also the order is of order n. So there is no intermediate state as well. And about 2. So that's first the start for math. linear sigma model, but more formal construction of this kind of model. So it appears there. Because in general, you have an infinite number of factors like this times this. And that's how you summarize this. But I have to admit that I don't understand very well. I don't deeply understand. My intuition says that because there is this number of interactions, then you can't put in a summarized way. So you call it covariant derivative. It's not related to H fields.
This would mean that you know all the different coefficients in probability.
Yeah, there is no Wilson coefficients here. That's what you're saying.
Yeah.
Yeah. The idea is that you know you have no three parameters unless of for this one. And this part you have no three parameters.
Question? Just, what's that? This pi is just a number, isn't it?
This pi?
This pi, yeah. No, the other one.
Which one?
Is it the high square? The pi of you?
No, it's pi times pi. Not a number. It's really set up. So because pi is a vector, so
I don't remember where this covariant, how this covariant derivative, how to derive it exactly, but of course it's related to the fact that pi transforms nicely on a sphere, and then you write, say, you could write, for example, the last component as square root of 1 minus the other ones, right, to get rid of the last one, and then you start computing, because of that you generate infinitely many terms. So you need to make sure that you have non-linearly realized. I don't know, Andrea, do you want to say a few words about this covariant derivative? Do you remember how to clean, let's say, what it means? Is it pi, f pi, or 1 plus pi squared?
initially you have this constraint, right? Initially you have this constraint, right? Of the pi, for the pi. For construction of sigma model.
Yeah, you write you write the exponential of pi dot the generator, right? And now you need to have something nice in terms of that group element. And when you start writing all possible terms that you can write for that group element that transforms nicely, you see that effectively you generate this covariant derivatives. Okay, so here I have an obvious question, which I confess I was a bit distracted as soon as you wrote this. I went to open his paper. I might have missed a little bit. So, we say that the degrees of freedom that we have at low energy are the pions, right? We don't have the quarks, they form pions, and we have pions. Putting pions and it looks like you are doubling degrees of freedom, that you have too much. You are keeping quarks and pions at the same time. For example, and maybe glue balls, you would put now a field for glue balls as well, but glue balls are made of glue, and now I have glue and glue balls at the same time. There is an obvious question, I mean, what exactly are we doing? Are we doing something, yeah, what are the rules of the game? Normally that's not physics rules, we don't do that.
Yeah, from what I understood, you want to consider pions with with, because they have small mass, you want to consider mesons massive and pion without mass in a different footing. And then maybe because you want to study, if you do things treating pions as composition of quarks, you cannot study moderate energy.
Right.
Now you can, because this effective Lagrangian, and you can.
So the last page of the paper is about concerns and remarks by Weinberg. Can you comment on those concerns and comments that he writes there?
I think.
What would you be worried? Of course, some things could work phenomenologically because you are putting the low energy stuff, and then because you want something at high energy, you keep some of the stuff that describes microscopics. It's very phenomenological, right? It's not rigorous, I think, unless you claim otherwise. But you could now put the rho, for example, right? The rho particle, and you could put the first blue ball, maybe, or the second, but not the other ones. And then you keep some irrelevant operators, right? This C d pi square is d pi square, not d pi square.
Yes.
D pi square you already have there.
Yeah.
So you are keeping some terms, but you are truncating.
That's
putting C1. So it's all a bit murky, it's not totally clean. What could be the concerns, and what should we be worried about? For example, if I compute something at very high temperature, and I count degrees of freedom in this theory, will I not get too many? Because if I were to try to go to very high energy, I have all the gluons that already, and the quarks that already make the mesons, but then I put extra mesons there. So maybe I could ask that. Isn't this theory bad at high energy? It's a bit funny. I'm not used to this, to integrating things out, to create degrees of freedom, and then keeping the things that we integrate out.
Yeah,
It looks exotic.
I think when you put it, you lost the possibility of to study high energy. That's what I think.
Doesn't he want us to study the interaction between heavy quarks, like the charm at the bottom, ions? Is there effectively? I imagine that if M is on the mass of the charm, then it doesn't make sense to integrate also the rho and the group, also they put at the same mass. We want to keep the lowest line below here, which are pi, but very massless. Keep all the stuff that are one order one that you see D, that you pick them from the UV.
Okay, good. So what quarks do we keep there? What are these Qs?
What quarks?
I think so. It's charm, the bottom. This is in my phenomenology, this exotic in the heavy quark sector. Maybe that was the motivation.
So you say it's U and D?
U and D.
Yeah, for sure there is U and D. The comment about creation of new environment will be
Interesting. Okay, we have to think about it. Thank you very much. Okay, last one. Who is left? Okay, Rodrigo. Please go on. Yeah.
So the paper I'm going to talk about today is called IFT-UNESP current model and variance at large end. Okay, so as we've seen in class, QCD at large N and low energies is described essentially by mesons. Mesons are the right degrees of freedom to describe QCD at low energies. And from the analysis of Witten, we've seen that baryons, at least large N, they behave like solitons, right? So what this current model program does is, let's try to write down low energy effective field theories with meson degrees of freedom. So we introduce this field U, which is an element of SU2. So where these are the generators of SU2 and pi are the pi fields. So this is SU2. And as I said, baryons should be solitons made out of this meson pi fields. So what we do is let's identify baryons with solitons in these curve models, which are the models in which the degrees of freedoms are these group value fields. Okay? Okay, so when we're looking at solitons, we usually have non-trivial topological configurations which are related to non-zero topological conserved charges. So what is the topological charge in this context? In this context, we have the following topological current, which one can construct out of these group value fields, which is, for obvious reasons, we call Pyro number. Where this L here, we define as this object here, which you can show that it's an element of SU2, of the SU2 algorithm of the group, whatever. So, as usual, this topological chart essentially counts windings of these field configurations of the unit. And so they take integer values as something, sorry, the charge, which is the zero component of this current, takes values of the integers. So this justifies calling it a number, a Baryon number. And we will, identify the number of baryons in our solid. I will focus on a specific Scrum model, which is what this paper does, is the BPS Scrum model, whose Lagrangian is the following. Which is again square. Square, you can see, plus a potential, a number, what's the parameter? A potential which depends on this number psi. This number psi is essentially, if you go to the pi space, so we have 3, pi 1, pi 2, pi 3, it's only the distance away from the origin. So that's the definition of the model. There are a huge plethora of Scrum models, but that's the Scrum model we are working with from now on. Okay, so it's called a BPS Scrum model. So why is it its name? To understand it, I have to talk quickly about something which is called the BPS bound. So usually when we have topological charges in our theories, which are related to solitonic solutions, so we have static solutions of the field equations of our theory, their energies are bounded from below, and this bound is related to the topological charge of a given solution. So so we have this bound that any static field configuration of our model should satisfy. And it turns out that this model is interesting because it is integrable. It has an infinite number of conserved charges, and one can then, using this property, construct an infinite number of exact solutions for the model, which are the following. So, of the following form. These are what people call the Hedgehog solution. So, this psi, which is what I already introduced here, is the distance of the pi field to the origin. Only depends on the radius, where now the radius is the radius in the real Euclidean space. And you also introduce another coordinate, complex coordinate u, which is so we're parameterizing this pi space in polar coordinates. So you have an r and spheres. You can always parameterize a sphere by a complex number through stereographic projection. And this u is exactly this complex number. So it parameterizes the spheres in this pi space. And it has it only depends on the phi. Right now, these are the angles in real space. And it has this following form. This is the form of the solutions. One can show by plugging these ansatz in the equations of motion that we have an infinite set of them, and this n, it's the Baryon number of each solution. So we have an infinite number of these solid solutions in this model, and it turns out that if you compute their energy, all of them saturate this bound. So for the BPS model, the solid in this BPS model, the energy is equal to what the BPS bound, what saturates the BPS bound. And if you take a look at how the solutions look like, for instance, if you plot energy density as a function of the radius, you see that they have the following behavior. So these solutions have compact support in space. So they indeed describe compact objects. And it turns out that they have some cool phenomenologies. For instance, since they saturate the BPS bound, their energy goes linearly with baryon numbers. So this is an experimentally verified fact for nuclear physics, and that's something that other curve models don't reproduce as well. Moreover, if you look at the size, the typical size of these solutions, you see that they scale with the baryon number to the 1/3. So the size of these objects go with the baryon number to the cubic root of the baryon number. This is also phenomenologically correct. These are two properties of this nuclei that these models describe. Moreover, you can pick this expression for the energy, fit with the data, and compared to other models, this model fits energy of nuclei very well using this formula here. And to end, one can show that the energy of static configurations in this model is invariant under volume-preserving diffeomorphisms. So in some sense, these baryons look like incompressible perfect fluids. And this is the third cool phenomenology. So there's an analogy with the liquid drop model for nuclei. So, I mean, to conclude, so I think this is a nice way of taking with this intuition that baryons are like solitons and trying to implement this in a real model to try to derive some properties of baryons. Of course, it's not an exact model, but I mean, it reproduces some properties of baryons.
Question?
Do you impose the bound on energy by hand?
No. That's something, I mean, you know that the model is integrable, you write the z-tested, plug them in the equations of motion, and then you have an infinite tower of exact solutions for the model, and you compute your energy and see that they saturate the bound.
So about this one also, so you wrote that there are BPS, and usually, like for example, you have supersymmetric theory, it comes from all the things that I can get where the bound comes from.
Okay, so I think it's the way we call these bounds BPS bounds in supersymmetric. I think this relation for topological charges came first, and then we see that we can associate these topological charges to something in extended supersymmetry algebras, and then that's why BPS came into the supersymmetry literature, the way I see it. But this comes out from picking, like, there's an expression for the energy, and we can show that it satisfies the exact equation. It's just computation.
I didn't understand. You said that you have infinite many solutions for the baryon number, so we have infinite many baryons.
No, I mean, a baryon number, so for the solution of number n, the claims that they're describing are a compact object of nuclear matter of baryon number n. So this would be more analogous to nuclei for larger, for big instances, like I don't know, 3 protons, then n will be 3, and this goes on. So it's a baryon for baryon number 1.
Your expression for the energy, you have the baryon number inside the model, so you don't have any information about the sign.
Yeah.
So the conclusion I have that the production of baryons and antibaryons will be at the same rate.
That's something we expect by symmetry, right? But I'm not saying anything about rates of productions of particles.
So the Barlow number is symmetric in this model.
Yeah, I mean, suppose you have a proton, another proton and proton. I think it is intuitive that they have the same energy, right?
They have the same energy.
Mass, I mean.
Okay. So, but the bump from to overcome this energy will be therefore the same for protons and antiprotons.
I mean, that's a subtle problem, right? Well, asymmetry of matter and antimatter. I don't think this model once has the can attack this problem. So.
Yes, that's alright.
So, what is a Skirm model? If you want to write your own Skirm model, what are the rules? As you say, there are many models. What would be any one?
Okay. So essentially what you do is you construct Lagrangians out of these L mu's right there. So, for instance, the traditional Skirm model would be something like proportional to L mu plus that's the time next. So you essentially write actions out of these L fields, and you can always increase the number of derivatives.
Yeah, so that sounds very good. So I have that will have all the right symmetries to transform nicely because you built it out of currents and you are just taking traces and so on. Okay, and what else? And okay, so that's point number one. You should think that I have the right symmetry. What else do you impose? That's it.
I think that's it, but then after that you start to look at phenomenology. So, for instance, for this model here.
Maybe I can talk about my confusion.
Okay.
Do you impose anything about, so you have this pi n field that we saw before inside this element Q, right?
Yeah.
Do we impose that this Lagrangian should reproduce pi in physics at low energy? If I expand around L being small, when L is small, should these Lagrangians become the Carroll Lagrangians that drives ions, or?
Not this Lagrangian, but for instance, Lagrangians such as these, I think they should, yeah. So, this case, there's a caveat. It's not a caveat, like there's a limitation. They say that it's only good for large nuclei in which you can neglect what they call the pion cloud around the nuclei, which would be this pion physics coming from these terms.
Okay, that was what I was confused. I mean, you start writing something and I don't see the leading terms for pion. I just see some cubic or 6-point terms.
You can neglect them for large nuclei because the pion cloud is very small compared to the bulk of the nucleus, and then this topological model can describe well big nuclei.
And how come psi is allowed? Psi doesn't look like it's built out of these currents. Psi looks like something funny, like the distance in pi is not. Contrary to these currents, psi looks like Anyway, it's a technical point. But I understood your point. So you construct things out of currents, and sometimes you want to mesh low energy, sometimes you say, for some reason, this is only for very high energy, and then you are doing phenomenology, so you can whatever. Any other questions?
Can you compute amplitudes easily with this model?
I don't think so. You can, At the end of the paper, that's something I've not gone into because I wouldn't have time. They quantize some rotational modes of these solitons and try to match with excitation spectra of nuclei, but it doesn't work that well. That's the only quantum thing you do.
Sorry, but I think you should be able to compute that. If this is supposed to describe the energy of this configuration, right?
Yeah, okay.
Why wouldn't you be able to take two far away configurations and send them at each other and see what happens?
Right, you're right. Nothing prohibits you from doing that. It's just that they don't do that. Very good. Class.
Yeah. Okay, so now we do the voting. Now we vote on the presentation, etc. And I need the connector to connect my computer to WISC. So can someone please go upstairs and get the connector from Luis? We need the connector to the projection. So think in the meantime about the scores that you want to give for physics presentation and questions. And I can stop the recording now.
Tem alguma discussão sobre